the last class we have seen a particular type of particular way of creation of a chaotic orbit. There in that system you had essentially two planes, two eigenplanes, and you had outgoing spiraling orbit in those outgoing planes, and they somehow interacted so that the overall outgoing behavior was arrested. From one plane the orbit got thrown into the other plane, and from there it got thrown back into this plane, and so on and so forth. So, that is how the chaotic orbit is organized. That is one mechanism. Today let us look at some other mechanisms of generation of chaos, just in order to get you comfortable with the idea. Today let us start with what is known as the Roessler equation, R-O-S-S, this is umlaut. Yeah, this is the German pronunciation, its pronunciation will be Roessler. You will have to make your mouth look like as if you are trying to pronounce O, but you will actually pronounce E. So, it will make that O umlaut kind of sound. It is Roessler. So, this man proposed a certain set of equations, not exactly in order to represent a particular physical system, but it was just a set of equations that has a certain property, which will be very interesting for us to study. It is simple linear equation. Simple linear equation. Here is a bit of nonlinearity, this zx term, except for that everything is linear. So, in a linear system you would expect the kind of behavior that you already know. So, in order, if I ask you to analyze this set of equations, what will you do? What will be the procedure? You will first locate the equilibrium point. Where is the equilibrium point? Is 0 0 0 in equilibrium point? Not exactly, because of this one. But of course, if you how many equilibria are there? Try to find. Both of them actually existing. Okay. Now, depending on the values. So, can you make a depending, you said depending on the values of C, relative values of C and X, right? C and A, right, yeah, C and A. So, under what condition would they exist, under what condition they would not? C is C by A is greater than okay, C square is greater than 4A. If that happens, okay, then you have, then they exist. If this is not true, then no equilibrium point, right, fine. Now, here in this system, since these two equations are perfectly linear, I might argue in the following way: this is a 3-dimensional thing, right? I will look from the top as if I am looking at the projection into the xy plane. I can do that. If I do that, then I see only this set of linear equations, right. And in this set of linear equations 0 0 is the equilibrium point, and by ignoring this I can find out just by looking at this, because if I am looking from there I will not see this, I will see only that, right. And I can more or less in a sort of highly simplified line of reasoning I can talk about the stability of that 0 0 equilibrium point in the xy plane. Okay. Here you see the Jacobian matrix will consist of -1 sorry, if you consider only these two equations, then it will take this form x dot y dot is equal to 0 -1 1 a. Okay. Under certain condition, if some condition is satisfied, then you would notice that this will become a outgoing spiral behavior. Can you find out that condition? Easy from this, just a 2-dimensional equation. So, what is the condition? What is the expression for the eigenvalue? That is it. Lambda is a plus minus a square minus okay, good. And the condition for stability is this term, okay. This term should be negative, then it is stable, else it will become unstable. So, you can easily see that it will become unstable at a is equal to 0, right, a is equal to 0, it will become unstable, fine. So, this is negative term, a is equal to 0 means it will be a purely imaginary pair of eigenvalues, and beyond that it will become spiral, outgoing spiral. So, you would expect outgoing spiral behavior. So, this is all you can infer by looking at only the projection, completely forgetting about what is happening in the z axis. Now, notice the character of the thing in the z axis. So long as x is less than c, so long as x is less than c, this is a negative term. So, depending on z, if z is, say you start from the z is equal to 0 plane, then if there is some amount of z, then it will create a negative rate of change in z, it will come down to the z plane, right. Can you see that? So, if x is less than c, then that is happening. Any deviation along the z coordinate will tend to die down.
But sir, the a value will also govern this.
Yeah, of course, but I am sort of making a hand waving argument to give an flavor. So, a value is there, but if a value is sort of overwhelmed by this negative thing, that will happen, okay. But then if x is greater than c, then you see a plus a positive number, so this fellow will tend to build up, okay. So, things will start to happen in the z plane also, right. As it happens in the z plane, as it goes in the z plane, here is a negative term, which means it will make x smaller, right. If x is smaller, then again, so you can see these become linked up, but essentially you start to get a feel of why things will not blow to infinity, right. If x becomes large, then z will tend to become large, that will again tend to reduce x, so on and so forth. Okay. So, this is something we can infer, that this fellow will tend to create a bounded orbit, clear. But then here you can see A and C are the two parameters, and these two parameters are in some books you will find A, B, C, they put the parameters this way, but for the sake of simplicity we have taken A to be the same, and there is an equilibrium point on that plane, right, which has become spiral. Let us look at the behavior there. Here you have see, I have started from just anywhere and it goes through some oscillation, and but finally it converges onto something that is almost on this plane, okay, right, almost. There is a bit of excursion along the z direction, but nevertheless it is a periodic orbit, it has created a periodic orbit. See, notice that first I argued that there would be a unstable equilibrium point with outgoing spiral kind of behavior somewhere here. So, it will tend to go out. Let us check, let us set this initial condition to be 0, 0 and very close to 0, 0.0001, okay, and let us restart the whole thing, see how it behaves, okay. So, you can see that here there was a plane, that plane I was talking about. If you look from the top, you will see this outgoing spiraling orbit that you see here right now, fine, but it has ultimately gone out, so that the nonlinearity will start having its play, and as a result of which there will be some excursion along the z direction, which will keep the whole thing bounded again, which means that this outgoing spiraling behavior could not really continue, okay. If you start from somewhere here, then let us see what happens. Where do you want to start, so that you can see the incoming spiral orbit, say x is equal to -4, y is equal to -6 and z is equal to -1, chalega. So, -4, -6, -1. Okay. See, it has converged onto that from the outside, which means it is a limit cycle. We have already talked about that situation where it is a outgoing spiral behavior on the inside and incoming spiral behavior on the outside. Ultimately, there is a closed loop behavior, a periodic orbit that is created, fine, convinced. So, it is a periodic orbit that is created from the outside, also it is coming in because of this feedback term here. Now, let us change the value a little more, let us see 3 and let us run it. I will better start from 0, 0, from the inside it looks better. See, have you noticed what has happened? No, not only the radius has increased, something more has happened. There are 2 loops now, okay. You see, there are two loops now. The one that I talked about as a period 2 orbit, right? This is a period 2 orbit, fine. Are you convinced? So, initially it was a period 1 limit cycle, now it is a period 2 limit cycle. If you increase the parameter even further, say see what you actually saw in the first computation. Okay. So, you can see that now it is still a period 2 orbit. Let us increase the parameter in steps. I am increasing in very small steps though. It seems to be still a period 2 orbit. Still a period 2 orbit. Fine. Okay. Is something happening? No, not yet. So, what did I do? When I am pressing this one, what I am saying the computer to do is, where it ended the last computation, you start from that as the initial condition, so that you delete all the initial transient, and then you will be able to see the final steady state behavior. Okay. So, as we increase it further, here you can see a lot of things happening, but is it really there? No, it is still a period 2 orbit. Still a period 2 orbit, fine. Now, I am making it 3.9. Something has happened. What has happened? It is now period 4 orbit. Okay. So, you see the period 2 now it has separated, and these were earlier together, now they have separated, and as a result of which it has created a period 4 orbit. Okay. Increase it further. How many? Still 4, huh? How many? Too many, right? But nevertheless a periodic orbit. Well, I can see that it was changing too fast. So, let me see what is in between. This is still a period 4 orbit. Okay. At 4.1 it is still a period 4 orbit. 4.15. Now, see the period 4, each of these branches have now broken up. As a result, it is a period 8 orbit, fine, and then it will enable you to understand what we saw at 4.2. It is period 16 orbit, right. So, we see a succession in which it was initially a period 1 orbit, then it changed to a period 2 orbit, changed to a period 4 orbit, changed to a period 8 orbit, changed to a period 16 orbit. Do you see? It is a progression, and where does it end? See, if you have a series 1, 2, 4, 8, 16, 32, 64 and so on and so forth, what does it end? Infinite. So, it is not really difficult to predict that going by this sequence after some time you will land in a period infinity orbit, or in other words a chaotic orbit. Okay. You can easily see, I will in one step change it somewhat more. Let me change it a little more so that you can see it clearly. 6 is better. Now, see the evolution, how it goes. So, as it goes outwards, it is thrown up and it lands inside, again it goes outwards and so on and so forth. So, you can increase it and see. Fine. So, you can see it has turned into chaos. So, what was the sequence in which it was going? In this case, you could clearly see that it was just not just happening any which way, it was going in a particular way, particular sequence in order to reach chaos. It was what is known as a period doubling cascade. It was following a period doubling cascade. Can you see the eigenplane, right? Even though the system is nonlinear, you can still see that more or less it is following the eigenplane here in this part, and then because of the nonlinearity it is going out. So, this is the character of the Roessler attractor. You can see it from various angles. For example, let's stop it. If you see from another angle, you can see what is happening. It is, you see the threads going up and coming down, it is like this. Okay. Do you see the structure? You might see it from various angles to make it clearer. Okay. Fine. So, you have the structure more or less clear now. Is it clear? So, that was one another type, another very clear example of how it happens, how it finally builds into a period infinity or aperiodic orbit. Okay. We will see why this happens, what is the mechanism in subsequent lectures. Right now, I will not explain why it went from period 1 to period 2, period 2 to period 4 to period 8 and not something else. Today, I will not do that, but later I will come back to this question. That is obviously a very pertinent question. Why does it happen that way? Why does not go from period 2 to period 3, for example? So, we will come to that. Let us now take up another very interesting and very simple system. It is suppose you have a pendulum. If it is simple pendulum, its equation would be, if say this is your x, the normal theta would be now called x, because that is the only variable necessary in order to only position variable necessary in order to specify it. So, it would be x double dot plus something times x dot, this is the dissipation term, plus something times x is equal to this is actually the forcing term, this is actually the sin x term as we have already seen. So, let us write it this way, that we have already seen that, right, g by L sin theta, that term comes x double dot plus c x dot plus sin x. Now, this will be very simple, is equal to 0 will be very simple. We have already seen its behavior. No, we have already seen its behavior would be that there would be an infinite number of equilibrium points, there would be those spiral inwards, then the saddle, again the spiral, again the saddle, so on and so forth. We have seen that. Let us make it a little more complicated. Suppose you have a forcing function that applies a force like so in the tangential direction. You might do it like this, that you have a point of suspension, and suppose this point of suspension is moved. That is one kind of forcing. That means the pendulum is hanging and here is a point of suspension and that fellow is being moved, right. Those of you who have done the dynamics of physical systems course, we take that derivation of that equation as one of the standard problems, very simple, but ultimately it leads to somewhat complicated equations. Let us not today land into such complicated equations, because we are not looking at the equations today, we are looking at the behavior. So, let us take the very simple system where the forcing is exactly in the tangential direction, and the forcing in the tangential direction can be a sinusoidal term. So, that sinusoidal term, let that be some amplitude k cos omega t. Okay. By the way, here there was a g by L term, which we have assumed to be unity. We have sort of scaled everything, as a result of which this sigma, which is the frequency of the forcing function, that has become a function of the natural frequency of oscillation of this fellow. Natural frequency of oscillation of this fellow was root over g by L. So, this is this is actually expressed in terms of that. In any case, ultimately we will land up this equation and we are trying to study the behavior of this equation. Very simple system, just a pendulum with some kind of damping and you are giving a forcing function. Let us study its behavior. Now, for that let us start up all over again. What the hell is this? Scan files, why? I will go to the driven pendulum. Okay. Now, here our parameter is the value of k here. So, let us start with say 0.4. See, it is homing onto a periodic orbit. Can you see that? It is a nice periodic orbit. Clear? So, it has become a periodic orbit. In what way? That this fellow is making it oscillate and the pendulum is also oscillating just like that. This closed loop here, is nothing but a oscillatory motion in the real physical system.
What will be the frequency of the oscillation?
This frequency of the oscillation, the forcing frequency really.
Forcing.
Yeah. Because here there is a natural frequency of oscillation, natural frequency, and there is a forcing frequency, but here the forcing frequency will dominate its behavior, and therefore, it will make it oscillate at that. Only when the the two frequencies interact in a way somewhat moving out of step with each other, you start to see other type of behaviors. Okay. Let us now increase it further, increase the parameter further. See, here it is still going into a nice periodic orbit. Happy? Is it completely true? In the sense that if I start from another initial condition, say -3 and 3, does it land there? Okay. This implies that there are actually two coexisting behaviors. You start from somewhere else, it goes here. You start from here, it goes here. Can you see that? So, it is not really just one oscillatory motion, there are two possible oscillatory motions of the system. These are two coexisting attractors, right. So, for such a simple system, you have coexisting stable periodic orbits. Stable in the sense that if you keep running like this, they stabilize onto these two orbits. Fine. Now, let us increase it further. Still periodic orbit. Still periodic orbit, starting from two different initial conditions. Oops, not coming anywhere, right? Okay, let us then, I saw that at 1.0 it was nice two coexisting periodic orbits, and then this fellow start doing these weird things. So, let us increase slowly, let us see. 1.1, it is still a, no, it is not coming to the same behavior. Can you see that? It is not periodic orbit yet. If you are not convinced, let us see. Not periodic orbit really. Let us allow it to run for longer time, see what happens. I want to run it fast so that I do not waste time on this. Both individual are not coming back to the same behavior. If you want to start, all the time you are seeing this. So, you see it has a large periodicity. Can you see that? It has a large periodicity. So, in between 1.0 and 1.1 something more happened. So, we need to increase in even more smaller steps. I am illustrating this because on various systems you will have to do this procedure. So, at this stage it is still a nice periodic orbit. Okay, now look what has happened. See, what is it now? It has really gone into a period 2 orbit, both of them. Can you see? There is a difference here. So, both of them gone into period 2 orbits, and if you increase it slightly more, in this system the changes are relatively faster. You notice that, see, it is now changing into period 4 orbit almost. Can you see that? So, here also you see a succession of periodicities, period 1, period 2, period 4, but here there is a additional complication that there are two very symmetrical attractors, but coexisting attractors. Okay, now we are in a position to change it significantly and see the result. I have changed it too much. Let's do it slowly. You will not be able to follow what is happening. No, it is going up in time. See, the blue parts and the red parts are getting mixed up. Can you see? They are no longer separated, they are getting mixed up. So, beyond a certain parameter value, starting from different initial conditions, their behaviors are different, all right. Their exact positions are different, all right, but essentially they tend to behave in a qualitative way in the same manner. They visit all parts of this attractor, which means that the two initial conditions, if you have two initial condition, the parts of the state space that they visit, they sort of mix up. This is called a mixing in the state space, mixing in the state space. If it is a periodic orbit with two different periodic attractors, then there is no mixing. Start from different initial condition, they go to different parts of the state space, while in this case you have a mixing of the behavior starting from different initial conditions, and this behavior is really chaotic. How do we make sure? In order to make sure, let us start the two orbits in from very close positions, 0, 0 for the red one. For the red one, it would be 0.00001 and 0. Okay. Now let us start it. See, you cannot distinguish them, right? Now you can. This is the hallmark of the sensitive dependence on initial condition. We have started from very close initial conditions, but ultimately they got separated out, which means that this behavior is a chaotic behavior. Just to recapitulate, what is the technical connotation of the term chaos? 1, it is a bounded behavior. 2, it is aperiodic behavior, and 3, there is sensitive dependence on initial condition. In all three systems that you have studied, we saw this property, that there is these three characteristic features. Okay. Now you see, the last days one of you had commented that if you have a chaotic orbit, I had said that then prediction fails. Why? Because in order to do the prediction, you will have to start from initial condition and solve the state set of equations to come somewhere there. And if there is even a minuscule error in the initial estimation of the state, then obviously there will be a large error in the estimation of the state after some time, for due to this particular reason that two extremely close initial conditions evolve completely differently. They exponentially separate out, and that is why prediction fails. Prediction fails not only because of our instrumental errors. Instrumental errors means if I want to measure the initial condition of any physical system, there will be some instrumental errors, which I represented in the last class in terms of a error ball. Okay. And we had argued that if this error ball reduces, then the prediction is successful. If this error ball, I am not talking just of the error ball expanding in size, but it is distorting in such a way that in some direction the distance is increased, then the prediction fails. Under what condition would the error ball increase in size? If you take the Jacobian, its determinant is greater than 1, then it will be increasing in size. Non-dissipative system, there is a energy input due to which things can blow up. But here we are mostly considering dissipative system, which means that this error ball will shrink in size. But even though it shrinks in size, it may sort of flatten out in such a way that in one direction it grows, in the other direction it shrinks, and the growing direction that will go to infinity unless something is done to it, and that something is where it is folded. That is the mechanism we talked about. Now, this failure of prediction does not happen only because of your instrumental errors. Suppose due to some way, by some means, you have accurately estimated the error, estimated the state. Still, how will you convey to a computer? As a real number. As a real number. The moment you want to convey to a computer as a real number, computer obviously has a finite length of any number. So, it will have to be truncated somewhere. You might argue that I may specify the initial condition by means of a rational number, which requires really a finite number of bits. You might argue that, but the fact is that in the real number space, the irrational numbers are dense on the real number space, which means that if you want to estimate it, in its neighborhood there will always be some irrational numbers, which means that this argument will fail. Ultimately, in order to specify that, you will need to write down an infinite number of digits in order to specify that, which is not possible. And therefore, both due to the instrumental error as well as due to specification error, there will be this error ball, and therefore, there will always be an error in the prediction of the future state. Now, this as one of you commented in the last class, you can still make a prediction to some time in the future, and how long the time is can be estimated on the basis of how far it goes off. These two initial conditions will go off, but there can be the question how far it goes off or how slow it goes off. Two initial conditions will exponentially diverge from each other, but that rate of divergence can be different for different systems, and depending on that we can confidently say that okay, for the weather 3 days hence I can predict with confidence, but not more. For another system I can say for the driven pendulum I can say that okay, 0.5 second hence I can predict with confidence. Obviously, that depends on if this error ball is round shaped, and then when it reaches here it takes this kind of shape, then it went something like this, and as a result you can say that here there is the expanding direction and here there is the contracting direction. In general, so long as we can represent it as an ellipse, I can easily identify the expanding direction as the major axis and the contracting direction as the minor axis, right. Then we can say that the separation between 2 points, let us write the separation, initial separation as x naught, delta x naught, the separation between 2 points, and that goes into delta x at some time t. Okay. Now, if these 2 points happen to be in this direction, then you can write it as delta x t is e to the power right. So, here is the term that comes in. sort of a linear approximation we are making here. You might say, you might argue quite logically that there is no guarantee that this lambda it really exponentially increases. Yes, may not really exponentially increase, but nevertheless, if at every point you assume that there is a local linear representation, then in that local linear neighborhood, you can see that there would be a, if there are two real eigenvalues, then the immediate evolution will be in terms of e to the power lambda t, and then goes here again e to the power lambda t, goes here again e to the power lambda t. So that this will go on as more or less like this. Only thing is that at every point this lambda may not be the same. Okay. So the answer to that question about how long can I predict essentially depends on this value of lambda. Okay. If this lambda is positive, we know that there will be exponential separation increasing. If it is negative, it will decrease. Fine. Okay. If it is positive, then it will increase. If it is negative, then it will decrease. So for a chaotic system, we can confidently say that one of the signatures of chaos would be that the lambda would be positive. But nevertheless, we can still ask the question, how chaotic? Some kind of a measure of chaos that will be given by this, the number here. The question is, how can we estimate this number in a physical system? Let us consider this issue. So let us talk in terms of two different representations. Suppose there is an orbit that going like this in the state space. So at every point I can locally linearize it. That means at every point I can write down the Jacobian, obtain the eigenvalues, and make a reasonable estimate of how this ball is going to change in shape. If it is a saddle kind of orbit, I know that it will increase in some direction, it will shrink in some direction, so that I can easily say that okay, as it goes, after some time it will take a shape something like this. And the way it evolved depended on the eigenvalues. So we can confidently say that the unstable eigenvector direction will be somewhere in this direction, and the stable eigenvector direction will be somewhere in this direction. Can we say that? Yes, more or less. So for small stretches of the evolution, we can represent the rate of divergence in terms of the maximum, the bigger of the two eigenvalues. Okay. If it is negative, then we know that it sort of shrinks. If it is positive, it expands, and therefore if there are 2 or 3 eigenvalues, the bigger one will represent the rate of divergence. Okay. So we can do one thing. A program can be, we suppose we simply look at the Lorentz system, yes, like this, start from this point and go on. As it goes on, at every point I am calculating the Jacobian, calculating the maximum eigenvalue, and since this is a nonlinear system, that will not remain the same. At every point the values might be a bit different. So we keep on keeping track of the maximal eigenvalue and then average it out over the whole orbit. Can you do that? Yes, we can do that. So that we get an estimate of this number lambda averaged over the whole orbit. We can do that. That number is called the Lyapunov exponent. Okay. So yeah, the concept is that as the orbit goes, at every point in the orbit, not at every point in the state space, but along the orbit. Why? Because if you look at this state space, this is an attractor, which means that start from any initial condition outside, it will converge onto this orbit, right, which means that if you start from two initial conditions outside, their distance will reduce as it goes homes onto this attractor. So it is not just anywhere in the state space, it is not averaged over the state space, it is averaged over the orbit. So as you go along this orbit, at every point you locally linearize the Jacobian, you obtain the Jacobian, obtain the eigenvalues, and keep track of the bigger eigenvalue, the one that is positive. So you keep on calculating that over the whole cycle as it goes on and average it out. Had it been a linear system, that would not be necessary, because then the Jacobian will be same everywhere. But since it is a non-linear system, this is necessary. That would represent the exponential rate of divergence of nearby orbits, that bigger eigenvalue. Fine. Now the actual problem is not this, this is trivial. Given a set of equations, you can always do that. But the actual problem is that often you have an experimental situation. From the experiment you have got some kind of a orbit, because you can measure at successive instants the value of the position and the momentum and stuff like that, or in case of electrical circuits you can measure the currents and the voltages, and thereby you can plot the orbit on the CRO screen. You can see the attractor, chaos and everything can be seen on the CRO screen. Now suppose there is a experimental situation like that, how are you going to measure the Lyapunov exponent? In other words, suppose I have got a set of equations that are not exactly, you are not very comfortable with linearized at every point. Let's take it like this. Can we take another route which will give us some clue about doing it on an experimental data set? Let us try to understand this question. What question am I asking? Essentially the thing is that at every point I have to locally linearize and get the eigenvalues. But of course I cannot do that unless I have a hold on the equation set. So let us try to formulate some other means of doing so, which can be applied also to experimental data where you do not have the equations. So in that case what we will do? We will start from an initial condition which will sort of evolve in the state space. We are trying to find out how nearby initial conditions diverge, and therefore we will have to take another nearby initial condition, say we take somewhere here. So this orbit, the blue one is the orbit, the natural orbit, or I should not say natural orbit, every orbit is natural, it is the orbit that we have calculated initially, and then we perturb it and then recalculate the orbit from here, as a result of which its distance will go on increasing. After some time stop the procedure and calculate how far it has moved. So this is my x naught and this is delta x naught, and this is my, I can now express it in that terms since I know the time. I can express it that delta xt is equal to e to the power lambda t times delta x naught. Okay, but this is only over this much. Can we do that over the whole? No, we cannot. Why? Because this exponent, this expanding direction will go on changing, and as we have already learned, it will fold. So after some time this expanding direction, if it folds, it will come back to a position near to it. Even though there is a stretching in the state space, the point might actually come closer, will it not? Suppose you start from another initial condition, it goes on in this orbit. Suppose after some time this fellow goes this way and that fellow goes that way, after some time they both come to one of the lobes, the distance reduces. You would not infer from there that the exponential divergence has stopped. No, it is still there. So, what we will do? We will then have to rescale the difference. After some time we have to stop it, and again we have to come to a point that is closer to this one. Again we have to evolve. We come to this point. Again we have to come to a point that is closer. Again we have to evolve this point. Again we have to find where the difference is. So, we have to go this way. Why? Because it actually folds frequently. That is the character of the state space of such systems. So, periodically you let it evolve, two trajectories, let it evolve. One of them is the what is known as fiducial trajectory, the trajectory is the nominal trajectory, and the other is the perturbed trajectory. So, the perturbed trajectory you allow it to evolve for some time, and then you rescale it in that direction. Do you understand that? Why do you have to put it in that same direction? Why can't you start here from another position? Because this has already aligned, this line has already aligned in the direction of the expanding direction. So, you take another point closer to this initial condition along the same expanding direction, let it evolve, the expanding direction moves, changes, again come here, take another point. So, do you understand the algorithm, the way you have to write it? From here to here the evolution is calculated by the set of equations by the Runge-Kutta method, and this one, these are also calculated by the same things, but depending on periodic rescaling, and again you have to evolve by the same method. Clear? Okay. Today let us stop here. In the next day we will see how this can be also taken to the experimental situations, where you do not have the equations to evolve, where you have just a data set coming from the experimental setup. Okay, that is all for today.